let me talk about some properties of the space of holomorphic modular forms. So I'm going to define M sub k and chi to be, maybe let me write it this way, F holomorphic modular forms of level n, weight k, and character chi. And we already mentioned that chi has to be a character mod n, because otherwise the notation chi of gamma that's not a character of gamma naught n. But there's another condition, which is that chi of -1 has to be equal to -1 to the k. And the proof of this is look at the action of minus the identity, which is in our group gamma naught n. And once you just write out the definition of what it means to be a holomorphic modular form, you'll see that if this is not satisfied, then you're doomed. So we need these two conditions. Now, the space, or the set of these modular forms is a vector space over C. And it has an inner product. The inner product is, if you do the inner product of f and g, this is going to be, again, called the Peterson inner product. This is the integral over the upper half plane mod gamma naught n. And then you have to stick a y to the k in here, and then you have f of z, g of z conjugate, and then the usual measure dx dy over y squared. You need this y to the k here so that this thing is gamma invariant, right? Because when you apply gamma, you're going to get essentially a y to the k over 2 from each of these. So the reason for this is that the imaginary part of gamma z is equal to the imaginary part of z over cz plus d squared. This is some elementary calculation, and it's useful to keep this in mind. So this inner product is called the Peterson inner product. And this Peterson inner product turns, has all the nice properties for this. I don't think this is a Hilbert space because it doesn't end up being infinite dimensional, but you can pick some orthonormal basis with respect to the Peterson inner product. And there is a subspace, sk and chi. This is the space of cusp forms. So M is the space of modular forms, and you might have a constant term. S, the space of cusp forms, is the subspace of M that where the constant term vanishes. When I say the constant term vanishes, what I mean is that these things all have Fourier expansions at infinity in particular. So well, they have to vanish at all costs, right? So for which the integral 0 to 1 of f of the scaling matrix of f dx is 0. Okay, and this is, it's easy to check that this is indeed a subspace with the structure of this vector space, and the Peterson inner product is Peterson inner product on this as well.